All right, let's get started. Review the homework first. It was pretty simple, should have been pretty simple. First question was kind of silly. 1 cubic foot of water. All you need to know is the specific weight of water, 62.4. And then it's good to show the unit analysis. We want to get in that habit. So the unit analysis would be, okay, this is what I have. This is what I'm using, water. And I want these to cross the volumes, right? 62.4 pounds. So that was pretty straightforward. Number 3 said a can measuring 4 inches in diameter, 6 inches high is filled with a liquid. And if it weighs 2 pounds, what's the specific weight of the liquid? So that's very much like what we did with the styrofoam and the steel. Same process. So you would calculate a volume. That's going to be either pi d squared over 4. That's kind of what I use. So I'm going to start using that. Because that uses the given number directly. 4. I don't have to do any divide by 2 thing. And then multiply by the length, 6. So that gives me the volume. $16. Divide. It's like the volume is 12.5, 12.5663. And then if we have a weight of 2, then that gives us both of the relationships of weight over volume. Right? 2 pounds over 12.566, I'll say 4 inches cubed. So just keep track of whatever your unit is you have for volume, whatever your unit is you have for weight, and that sets up your specific weight. This gives it to us in pounds per inch cubed, right? Often we want pounds per foot cubed, so either one of those works. This number is, I get 0.1592 pounds per inches to the third for a specific weight. And then if I wanted that in feet cubed, I would just need to convert feet cubed. Anybody get that number? What'd you get in feet cubed?
45.93.
45.93 pounds per foot cubed. So that's just a factor of 12 to the 3, right? Yep, 12 to the 3 times this number should give you that number. Why do we like this number? Pounds per foot cubed is more common in the tables. So if we're comparing it to water, which we do a lot, that would be specific gravity when we compare it to water. Then we're going to need it in this unit, pounds per foot cubed. Let's see if I get that. 12 3 times. Yep. Good. Questions? It's simple. The next one's the same kind of problem, number 4, just using a different unit, right? We're using the metric system. So we have to come up with a volume, and then we have to come up with the weight, which we're given, 450 newtons, 20 centimeters, 10 centimeters, 15 centimeters. So we can come up with our volume and our weight to get our specific weight. So 450 newtons over, and then this volume, right? Which is just 15 centimeters times 20 centimeters times 10 centimeters. I get 0.15 newtons per centimeter cubed, right? So probably the more common unit is going to be newtons per meter, right? Because that's going to be what's in the tables, or maybe kilonewtons per meter. So we should practice getting this to meters. So if I have 0.15 newtons per centimeter cubed, then I just think about the conversions and I put those conversions in a position that'll cancel the centimeter cubed out. How many centimeters per meter? There are 100 centimeters per 1 meter, right? There's 1,000 millimeters per 1 meter. So that's, remember, it's 100, 1,000, and 1. So this is the conversion for 1 centimeter and 1 meter. If I want it to the third, to the third, to the third, I put everything to the third. So I've got to have a factor of 100 to the third to get these centimeters to the third to cross out. That gives me newtons per meter to the third. So just move the decimal place, what, like 9 times or something? 0.15, enter 100, and a 3 factor times 6 times. Move the decimal place 6 times. 150,000. Right? Yeah, so then if you wanted just to keep the unit conversation going, sometimes we might want kilonewtons here. Depends on the table that we're looking at and what we're comparing things to. So if we wanted kilonewtons, then again, we just have to do a conversion from newtons to meters to the third. All right, anybody get that number? Good, good. All right, and the last one, SAE 30 oil. This is 30 weight oil. We'll talk about viscosity probably on Wednesday, but for now, that's what this stands for, 30 weight. So this is like engine oil, right? The oil you put in your car. Yeah.
SAE.
SAE is a call out for the organization that gives you the viscosities, testing organization, standards. I don't know what the acronym is, but it's a group. It's like ANSI, right? American National Standards Institute gives us all of the ANSI standards. This is like petroleum industry standards. All right, so they gave us the specific weight at 57.4 pounds per foot cube, which is kind of, it's not too far off of water, 62.4. But then they asked for the specific gravity. And remember that that's just a comparison of a substance to water. So you take your specific weight of your substance, divide it by the specific weight of water, and it gives you your specific gravity. So it's going to be 57.4 pounds per foot cube over 62.4 pounds per foot cubed. What'd you get?
0.91987.
Sounds right. I'd say, because if it was 62 over 62, that'd be 1. So anything smaller is going to be a little less than 1. 0.98987. We're going to do our rounding 92. And what's the unit of specific gravity?
It's perfect.
Careful. What do these units look like? Unitless. It's just a number, completely unitless. So it's pounds per foot cubed divided by pounds per foot cubed. Cross them out, unitless number. It's really a ratio, right? So if you have numbers greater than 1, then you have a substance that is kind of heavier per unit volume than water. If you have a number that's less than 1, then it's a substance that is lighter than water. So when we talk about buoyancy and things floating and substances, like what kind of substances float on top of the water? Well, oil does. If you put oil in water, it floats on top, right? That's because it's less than 1. If you have a substance that has a specific gravity greater than 1, then that's going to sink to the bottom of the ocean type of thing. All right. Promise they'll get more difficult. These are not too difficult yet. So, all right, turn them in. Collecting right up here by Cassidy. She's our homework collector first. Yeah, I want the little lab too for the styrofoam. Any questions on this? Got this down? We didn't have a quiz on Friday. Did anyone look for it?
Gotcha.
It didn't come available, did it?
No.
No. Sorry about that. How come you didn't email me and say, hey, where's my quiz?
I
It's because you didn't want a quiz. I get it. I wouldn't have either. All right. Sorry about that. That's kind of how my life with Blackboard goes. But we will have one this Friday, and I will remind you on Wednesday, and then I will send you a reminder on Friday that the quiz is available. So we'll do our first quiz here. All right, let's just cruise through chapter 1 and kind of wrap it up. So this is the new book now I'm looking at, but I don't have yet, but I have this online version, so that's kind of nice. Chapter 1 is like this beginning part of fluid mechanics. Chapter 2 is viscosity, which we'll do a little bit of on Wednesday. We'll just talk about it. Chapter 3 is pressure measurement. I'll probably do a little bit of that on Wednesday also, because I really want to get to chapter 4 fairly soon, because that's where it gets kind of good. Like that's where we actually can start to calculate some things with fluid pressure. And then buoyancy is a great chapter. Bernoulli's equation is a very good chapter, and we'll spend a lot of time there. And then the general energy equation, and then the Reynolds number and laminar flow, turbulent flow. So chapters 3, 4, 5, 6, 7, 8 are great. I want to get to those chapters. So we're going to kind of cruise chapter 1 today and get it done. And then we'll probably do all of chapter 2 on Wednesday, because viscosity, we're going to use viscosity, but we don't really need to study viscosity. It's a fluid property, right? It's how slick it is. So anyway, that's the plan. But right now, let's get through the rest of chapter 1. We kind of did the first part, no problem. We talked about weight and how we get weight, and that's mass times gravity. We talked about the units, and those are important to kind of continue to play with, especially this slug thing, right? Pound second squared per foot. That we need to kind of keep track of. Kilogram second squared per meter on the metric side. So most of the time when we do like a gravitational constant problem, we'll toss in those units to make sure everything cancels out. I'm a little surprised they didn't do a conversation about the metric versus the English system, but I think they have that. Not in the references, not in the internet resources. Yeah, maybe they don't. Anyway, let's do temperature, talk about that. We don't often have a lot of reason to convert between temperatures, but we should understand the basic concept between the two temperatures that we use the most, Celsius and Fahrenheit. Both of these are US temperatures, so a lot of people think the Celsius is metric. It's not. Kelvin is metric. Celsius is just a different scale. Now, a lot of countries use Celsius. We use Fahrenheit. So But that means that we need to understand both because equipment comes from everywhere. Equipment that we use in the fluid power area, you know, hydraulic rams, hydraulic pumps, they can come from anywhere. So then when you get the literature for those pumps or that hydraulic system, it could be in Celsius. So the big difference is Celsius freezes at 0. Water freezes at 0. And it boils at 100. It's a lot more straightforward than Fahrenheit, right? 0 and 100 is pretty easy to remember. It's going to freeze at 0. So if you have a negative Celsius temperature, that's below freezing. That's kind of nice to like remember. Fahrenheit's not that way, right? 32s are freezing. So 31 is actually 1 degree below freezing, but it's not negative. It's 31, right? So it's a little more complicated to keep track of the Fahrenheit and where what things happen at. Water boils at 212. It freezes at 32. Celsius, 0 and 100. And then the basic formula to go back and forth is right here. Again, I don't see us having a lot of need to convert back and forth. If we get a problem with Celsius, we'll work it in Celsius. If we get a problem in Fahrenheit, we'll work it in Fahrenheit. But those two equations are here in the book if we need them, if we need to go back and forth. The other two scales we have are these absolute scales. These actually we'll use when we get deeper into fluid mechanics and we start talking about increased pressures, high pressures, and temperatures associated with those high pressures. So that's where the Kelvin and the Rankine temperature scales come in. These are called the absolute scales, and they start at 0. So Kelvin starts at 0, and at 0, there is no molecular motion. So if you don't remember your chemistry or your physics, all objects have molecules that are moving. So this calculator right here, even though it's a solid, there's a little molecules in there, and those molecules are vibrating. Very, very, very small vibrations, right? So they developed these scales to go really cold. Like Celsius and Fahrenheit don't work as well when you get really cold, but these absolute temperatures, 0 is that absolute 0 temperature where there's no molecular motion. And then from there, it's just a scale that moves forward. And actually, the Kelvin scale moves at the same rate as the Celsius scale. It's the same increment of temperature. So it's just a scale that allows us to go a lot colder. And then the conversions are here to get from Kelvin to Celsius, 273.15. It's an addition, right? So if you have temperature of Celsius being 0, then you have 273.15 Kelvin. That's essentially the difference. That is all in this chapter if we ever need to convert back and forth, which again, like I said, I don't think we're going to need to have to do that. But we should be familiar with these temperature scales because we're going to get some of these properties at very cold temperatures or very hot temperatures. And these scales work better. And the tables use them, so we might have to interact with them. It does some example problems here. If Celsius is 33, how much do we have in Kelvin? So you just do the math, right? You just add 273.15 to it. We get 306.15 Kelvin. So it's like the Celsius scale, and it's just slid. You know, it's just the whole scale is slid 273.15. The Rankine scale is the exact same for the Fahrenheit side. So they did it for both sides. So if you need to, like, if you're given a temperature that's in Rankine or Kelvin, know that you can go to this first chapter and figure out how to get it to Fahrenheit or Celsius so you can have a feeling for it. All right. Not going to work any problems in that. The units we've talked about all the way through, they do have a nice table of units here. So here's our slug right here. And here is our unit that is equivalent to the slug. So that's how this table works. You can look things up. So if you're given, I must have mucked it up. Did I muck it up? Oh, sorry, man. All right, put the code in backwards. It's a new code. All right, so anytime you're given a unit that you don't know, like if you're given a unit of joule, you'd be like, oh, what was that, right? And I want to put the breakdown of a joule into an equation. This is a great table for that. So joule is a unit of energy, and it's a Newton meter or a joule. And it's also equivalent to a kilogram meter squared per second squared. Okay. So the units are going to get complicated. You're not going to remember what they stand for. I don't expect you to. This is available to you to look things up and convert them to the unit necessary. Mass, which we've been talking about on the metric side, is a Newton second squared per meter. On the slug side, pound second squared per foot. If you're trying to get units to work out, you're not going to want to put slug in there. You're going to want to put pound second squared per foot. All right. So just know that this is here. Density, reminder of how it works, and the units, specific weight, and a few other things that we'll get to. We'll do power. So hopefully they have horsepower. Yeah, here's the horsepower right here. Because a lot of our pumps and motors come to us in horsepower. So what the hell is a horsepower, right? Well, it's a unit we used a long time ago. It was a single horse. That's how we got it. So then they said, well, after we moved along and got into other units, they're like, well, we'll still use horsepower, but it means it's a pound foot second, right? A foot pound per second. And we'll talk about foot pounds a lot. So just remember this table's here when you need to go back and look something up. It's pretty handy. And I'm glad the book has it. Statics book has it really good. The previous fluids book had nothing. It was terrible. So that's pretty handy. All right, let's talk about pressure. That's the one I want to get to today. I think they use small p. Is that what that was? Yeah, lowercase p for pressure. Simple equation that we use over and over and over. It's going to be force per unit area. And force typically is in pounds or newtons. Okay. So force per unit area, pounds per foot squared, maybe. Area, remember, is it going to be in a unit per squared, or it's going to be in pounds per inch squared. So they have fluid pressure we're going to talk about, and then there's just pressure due to a force. Like me standing here, my body weight is acting on the concrete, acting on the bottom of my feet, and that's creating pressure. So any force that's distributed over an area is going to be a pressure. Also, fluid creates pressure on objects that are underneath the surface, like shown there, or actually that are on the surface too. So the unique thing about fluid pressure is it acts in every direction. So not in just one direction. Like me standing here, the pressure is acting down and then the ground is pushing up on me. So that's only two directions. But when you put an object under a fluid, it gets not equal pressure. It gets pressure from all directions, right? if we have an object that is not tiny, maybe that one's tiny. So if I have a fluid and I drop down a box, and I put this box underwater, it does feel pressure in every direction, right? That's how fluid works, fluid pressure. Well, maybe I can get a three-dimensional one, yeah. In all directions, right? But the pressure is relative to the depth of the fluid. The deeper you go, the more pressure you have. You maybe experienced that if you've dove underwater and had to equalize your ears. As you go deeper and deeper, that pressure gets more and more on your ears, and then you have to pop your ears, right? And then if you go deeper and deeper, you got to pop them again because the pressure is increasing as the depth goes. So the pressure here at the top surface has everything to do with this elevation underwater, right? So I'll call that H1. The pressure at the bottom surface is different. I'll call it H2, and it's going to be greater, right? So the pressure here, smaller, the pressure here, greater. If it's a lot of depth between the two, then the pressure is quite a bit different. You know, if it's feet, if I'm floating in the water vertically, my head's feeling much different pressure than my feet, 5 feet away, right? 5-foot depth change is a significant amount of pressure. So that means when we're underwater, we have actually more buoyant force pushing up if we have a surface area there, and less force pushing down. The side forces are all equivalent. We feel pretty much the same thing because those are all at the same elevation, right? So that's kind of how fluid pressure works. I guess I'll call it solid pressure, or just pressure due to a force. Works a little differently. Like if we take an object, maybe it's a house, right? And what do we build houses on? Anybody know? A lot of times we put them on concrete, but then the concrete does what? Sits on soil, right? So the weight of the home is pressing down on the concrete, which is pressing down on the soil. It's a lot of weight. I mean, we can estimate it at 100,000 pounds. A whole bunch of weight. Why doesn't that just sink into the soil? Hopefully it doesn't just sink into the soil. It's not what we want our house to do. The soil fights back at a soil pressure. In our area, an average soil pressure, not great soil pressure, but average, is 1,500 pounds per foot squared. That's a standard soil pressure, right? Where my house is built, it's 2,500, the soil pressure. So a little better soil. So a wetter area is going to have less soil pressure ability. It's going to be more like, it won't be mud, but it'll be wet, right? Just a wetter environment or a different type of soil in that area. I have a lot of clay where my house is, and clay is very good at resisting load. So before you build your home, before the engineer designs that home, he has to know soil pressures. She has to be able to calculate how much load and how much foundation is required. So we put our foundations, typically they look something like this, where they have what's called a footer. And that's a wide area to the concrete at the bottom. And the reason we have a footer is to spread that area out, right? The more area we have, the lower the pressure is going to go because it's pound per foot squared. And if we increase the foot squared, that number goes down, right? So this solid pressure thing is everything to do with a force and an area, right? So if I have a weight that is 100,000 pounds. And I have soil pressures. The pressure is equal to 1,500 pounds per foot squared, right? So that's like my P. And this is like my force here. I just need to know, like, how much area do I need for this equation to work? So the equation F over A equals P can be worked in a lot of different ways. And this way I'm saying, okay, the limit to my pressure has got to be 1,500 pounds per foot squared. The force is 100,000 pounds. How much area do I need? How do we calculate that? How do we get the area? Algebra, basic algebra, right? So I'm going to move it over, move the P over. Area is going to equal 100,000 pounds. Oh, a few zeros are missing there. 100,000 pounds divided by 1,500 pounds per foot cubed, right? The pounds cross, what happens to the foot cube? Goes up, and I'm going to be left with some number foot cubed. $100,000 divided by 1,500. I need 66.66 feet squared. That's how much area I need to carry this 100,000 pounds. It's not that much area. It's pretty small. Right? So this whole pressure equals force over area. In this case, I knew the pressure, 1,500. That's the soil pressure. I can't go over it, right? I knew the weight of the object, the house weighed 100,000 pounds. So I just needed to be able to calculate the area to make this equation work. If I know the force in the area, I can come up with the pressure. And then maybe I could compare that to some table. But this equation, pretty fundamental. We use it a lot. Does that make a little bit of sense? Yeah, so when you have soil pressures, that's a very civil engineering thing, but when you have soil pressures, those are your limits. You can't go over it, right? So we need at least 66.66 feet cubed of area to carry that 100,000 pounds. We've got to have it. So however we design this home, we need that much area of concrete so it will not sink into the soil. All right, let's look at the book. The book talks about this pressure thing, right, of a fluid. Since it is fluid mechanics, we'll do more fluids than we will solid pressure. But it's the same concept. Like if we have a furnace duct, furnace is your heater in your home, pushing air, right? That air is under pressure. The only way we get that air into the room is we blow it with a fan. So that creates pressure in your duct system. That's the system that delivers the air to the register where the heat comes out, right? On some older homes, the primary return, they get pretty big. So we blow hot air into the home, and then there's a cold air return that grabs the cold air and takes it back to the furnace. So essentially are recycling your air in your home, right? Well, this cold air return, it's usually pretty big. Like it can be 2 feet by 1 foot, and it's that sheet metal, really thin sheet metal, and it runs under your home or in the walls of your home. In old homes, it's in the closet kind of thing. Well, when you fire that fan off and the pressure gets created, the sheet metal on the edges can pop in and out, and you can hear it go bonk. Like an older furnace you can literally hear the pressure expand this ducting system, right? Because they did use rectangles for a long time. Then they went to round for the same system, and the round ones don't pop in and out. The rectangular ones, these long sides will pop in and out and kind of sound like a drum. Bonk, they'll bonk when it comes on. But we use this pressure thing for a lot of different things, like reservoirs of fluids. That's going to be all pressure calculations, like how much pressure is on this slope, how much pressure is on the bottom, how much pressure is on the sides. So we'll calculate that when we get to that chapter, the one I want to get to fairly quick. Swimming pools, dams, great pressure problems. And then fluid power systems, this is like a piston. So when you increase the pressure in here, it'll move this piston and it'll do work for you, whether it's a piece of equipment or a steering system in your car, same kind of thing. Brake system in your car. When you push that pedal, it is pressing on a piston that is pushing hydraulic oil to your brake. When your brakes leak, your brakes don't work so well because it's losing that fluid pressure, right? So yeah, we'll look at all of those. Here's an example of a cylinder. So it has a load and it has fluid, and then here is the piston, right? So this becomes the surface area. So if we have, let's look at it. If we have a fluid pressure, or let's calculate our pressure. So we have a piston. I'll draw it horizontally. A little easier for me to draw. So here's the chamber. Here's the piston. Here's the rod that comes out. And this is it's gonna push to create some kind of work. So who knows what it's gonna push on something, right? So then we have these ports that come in and we send fluid into this chamber, right? And this is a closed chamber for now. So then when we push fluid in, it pushes on this surface. So if I go in with 10 PSI, that is pounds per inch squared, I can figure out how much load I can move if I know the size of my piston. So we'll say this piston, we're going to make it pretty big. We're going to make it a 6-inch diameter, right? So we're going in with 10 PSI fluid. And that's coming from a pump. And we can just go into a catalog and pick a pump, right? That'll give me 10 PSI. Goes into this chamber and it's going to move this cylinder. How much can it push is the question. How much load can we move? Well, if we have 10 pounds, right? 10 pounds per inch squared, we should be able to calculate inches squared. How many inches squared do we have? Because every inch squared, we get 10 pounds. That's how fluids work. That's how fluid pressure works. 6 inches in diameter, we can calculate that area. And of course, the equation I use is pi d squared over 4, because that allows me to use the 6 pi 6 squared over 4 to calculate the area. It's going to be a fair bit of area. What do we get? $28.274. Somebody needs to check me on that. I get it twice. Well, that's good. Right? That's our area. So the equation for pressure is force over area. I'm given the pressure, 10 psi. And I want to know the force, F, and I know the area, 28.2743 inches squared. And remember, the 10 psi is what? It's pounds per inch squared. We wanted to know force, F. How do we get it? Algebra. Solve for F, right? That's just a straight multiplication. F equals not 280, 282. So 282.743 pounds. Everyone see that? It's how your car works. It's how a combustion engine works. It's not oil or water that we're putting into your engine, though. It's a mixture of air and fuel, right? Air and fuel comes into your chamber, spark plug lights it off, an explosion happens, which pushes a piston, which then turns a crank, which then turns your wheels. Same exact system, and they're using the advantage of this area thing, this surface area. We only had to put 10 psi in there. 10 psi is a small amount of pressure, and we're able to move 282 pounds. It's a huge mechanical advantage. And it's absolutely why we use pressure for so much. They go through some example problems, but really the whole quest is to understand this P equals F over A. The pressure is equal to some force over some area. If you know the pressure, then you can calculate either the force or the area. But just like all algebraic equations, you've got to know two of the three things. So if it's P equals F over A, we've got to know two of the three things before we can calculate anything. Right? All right, let's do another one. So we have a tank of water. And this tank is, oh, sorry. Thank you. You gotta tell me that right away. Perfect. Big tank of water, 60 foot in diameter and 100 feet tall. And the question is this gonna sit on concrete? So we're gonna pour concrete, make my little concrete hatch, and then sit it on soil that is rated at 2,000 pounds per foot cubed. So our soil pressures are 2,000 pounds per foot cubed, and it's water. And we want to know if this system's going to work. Like, is it going to be too heavy? Is it going to sink into the ground? Or is it going to be good? And our pressures are fine. So we're going to make the concrete the same size as the tank for now. We'll see how that works. So what you have to calculate is how much pressure is coming down on the soil, and is 2,000 pounds per foot cubed, sorry, per foot squared. Is that enough? Right? So calculate how much pressure is on the soil, and we're going to compare it to the 2,000. What's the specific weight of water? Yep, 62.4. What's the unit? Yep, feet cubed. So what do we got to do first? We could calculate the area first. That'd be fine. We're going to need that, right? Yeah. So the area looks like this, looking at it from the top view. And what's our diameter? 60 feet. So that's the area that this water is going to act down on. So let's calculate that area first. Anybody got a number?
Or 2,827.4.
Yeah, me too. And that unit is feet squared, right? So that's our area. Now what do we need? To come up with the pressure, P equals force divided by area. If we want to know how much pressure this is creating, what do we got to know? Force. Well, that's not force. 62.4 is not force, but it is force per unit volume, right? So how are we going to get to force? Huh? This is the specific weight, agreed. But we have to do something with it because that's not force. That's the specific weight. How much does the water weigh? That's what we need to know. Well, it weighs 62.4 pounds per cubic foot. So how many cubic feet do we have here? That's the question. How much volume is there? That gives us weight. So we have to calculate volume. And what's the volume of a cylinder? Right, that is 60 foot in diameter and is 100 feet tall. So it's area times length. Well, we did area. We have that number. Should put the unit on there. We just need it times the length, 100 feet. That's just moving the decimal point 2 places. So volume equals 282743.33 feet to the third. 1, 2, 3, 282,000. It's a lot of volume. It's a lot of water. It's a big water tank. Everyone see where I got that? Okay. Now you know the volume, you know how many feet cubed there are. For every foot cubed, you've got 62.4 pounds, right? So weight is going to be the specific weight, right, times the volume. So specific weight of water, 62.4 times the volume. 282743.33 feet cubed, and the feet cubed cross, and we're left with weight. Our number is going to get huge. Seventeen 643 183.79 pounds. $17 million, right? Okay. That was a lot of weight. And what's that weight acting over? An area. Right? That's how we get to pressure. Pressure equals force over area. Weight is force. So we have our 17,643,183.79 pounds acting over an area of 2827. Feet squared. I get a pressure of 6239. Is that right? Somebody will have to verify me. Yep. 6,239 pounds per foot squared. Right? That's this weight of water over its basically its footprint. Right? How much it's in contact with the soil. What was our allowable soil pressure? 2,000. And we calculated 6,000. How's our tank doing?
Some,
Not good. It just sank into the soil, big time. Probably didn't stop. Like it's the center of the planet kind of thing. So that means our area is just not big enough. So concrete that matches this big, massive water tank, it's not enough area. It's not enough area to create 2,000, right? So the way to fix the problem is to say, okay, the weight's not going to change. The water weight is the water weight. It's not changing, right? But we can change this area. We can make the area bigger, right? I guess it was a bad idea to make the area the same size as the tank. We need the concrete area to be like out here somewhere, spread out, spreading that load out, lowering the soil pressures. How much do we need to spread it out? Well, the way to solve, once you figure out like, oh, this is not going to work, we need to change the area. This area is not going to work, right? And we need to put the area in as a variable. So we calculate how much area is going to be needed. And then we set our soil pressure to what? 2,000. The thing that we need. So 2,000 will equal our weight, 17 million, over unknown area. Right? That'll give us this new area that should work. So the 2,000 and the area just swap places, and we say the area is equal to the force divided by the pressure. So that's going to be our 17 million. 643,183.79 pounds divided by 2,000 pounds per foot squared. And we can calculate an area that'll work. Because we determined the area that they wanted to use absolutely would not work. 17,643,183.792 divided. How much area do we need? 8,821.59 feet squared. That's how much we need. So where we had 2,800 before, we really need like 3 times that amount. So it doesn't sink into the soil. All of that's calculated just because of we know this pressure formula. P equals F over A. Right? Now, if I wanted a round foundation, I'd have to take this area and figure out the new diameter, set it equal to pi d squared over 4 and solve for d. But we don't have to do that. We now know we need 8,821 square feet underneath that tank. About 3 times the amount that we had before. And that should keep it from falling into the ground, right? Sinking. And we can go right to the soil pressures. There's no factor of safety there. We can use it right to those pressures. All right, that was a lot. Seems like such an easy, simple formula, right? It's just, again, it's just pressure equals force over area. But anytime you have a formula like this, you can solve it 3 different ways. You can solve it for pressure, you can solve it for force, or you can solve it for area. So the question can say, hey, I have this much pressure and this much weight. How much area do I need? Right? Or it can say, I have this much pressure and this much area. How much force can I hold? Or the way it's given, hey, I have this much force in this much area, how much pressure is that? So 3 different ways. All right. That's pretty much the definition of pressure. You're gonna do some homeworks. They are 16, 24, 47, 48. You don't have to write it down, because I already made copies for you. But if you're not here, I guess you gotta write it down to find those. That's these. Out of the new book. And this will be due Wednesday, yep. So same vibe, every Monday and Wednesday, we'll go over homework first. Try and get all the questions answered, start into new material, do some example problems. Then we are done. All right. Good luck with that. If you have any questions, you can email them to me or come find me today or tomorrow. So, all right, we good? All right. I will stop the recording. Oh, maybe I'll show this. It is in Blackboard too, though. But that is the questions.